Welcome back to geometry for one more video on section 19, similarity. In the last video, we took a look at some theorems for similarity of triangles, right? Conditions for similarity. So we took a look at angle, 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 which we proved using the basic proportionality theorem. And then we followed that up with making a comment that we can have angle, angle, which would give us similarity because as soon as we know two of the three angles, we in fact know the third angle in a triangle. We can also use side angle side, but instead of the traditional side angle side that we would think of for congruence, that doesn't make sense, of course. So we would want the congruence of an angle, but then the satisfaction of the proportionality for the side lengths, specifically two pairs. And then we can look at side, side, side similarity, and to satisfy that, we're looking at the proportionality being satisfied by all three pairs of sides. So if we have congruent angles and proportionality satisfied for the adjacent sides, we have similarity. If we have congruence, not congruence, but if we have the satisfaction of proportionality for all three pairs of sides, then we have similarity. So let's use those to help us with the following example. If we have that M and N are the midpoints of BA and BC, we want to prove that MN is parallel to AC. Of course, if we could use the basic proportionality theorem, this would be almost immediate. So we don't want to use the basic proportionality theorem. We want to sidestep that briefly. So in order to show this, in order to show that MN is congruent to, that MN is parallel to AC, what we could do is we could observe that AB is a transversal and that these two angle measures should match. So if we can get that triangle BMN is congruent to triangle BAC, then we would have exactly what we're looking for there. So that's a process that we're going to follow. So for our proof here, of course, begin with the givens. M is midpoint of BA and N is midpoint of BC. All right. Next, let's observe what the definition tells us. So by the definition of midpoint, we have that, let's see, we would want BM is equal to 1/2 of BA, BM is half of BA, and BN is half of BC. And that's just by the definition of midpoint. Once we have that, we can do some algebra to show that BM over BA is equal to 1/2. And that BN over BC is also equal to 1/2. Once we have that, right, they're both equal to 1/2. So by the transitive property of equality, we have that BM over BA is equal to BN over BC. Excellent. So we have that BM over BA is equal to BN over BC. That gives us side lengths and side lengths, but of course, the measure of angle B is congruent to itself. So since angle B is congruent to itself by the reflexive property of congruence, then we can say that we have similar triangles because we're satisfying side, angle, side. So triangle MBN is similar to triangle ABC by side, angle, side. Similarity, oh, that was more than I wanted to get rid of. MBN is similar to triangle ABC. Side, angle, side is being utilized, but we want to make sure it's clear that we're looking at similarity here. So we need the two conditions. Let's see, what did I say? It should be the congruence of angles and then the proportionality. So let's say it's 5, the congruence of the angles, and then 4, the proportionality is satisfied. Once we have that, we have that angle BMN is congruent to angle A by the definition of similar triangles. Which leads us to, right, we have that corresponding angles are congruent where two lines are crossed by a transversal. So by the corresponding angles corollary, we have that MN is indeed parallel to AC. The corresponding angles corollary. Excellent. So we can use the similarity for such things. All right. A really brief comment about the activity. Just that I think the directions are pretty clear. So if you have any questions after reading the directions and trying to attempt the activity, please let me know. Right? Send me an email, stop by during my office hours, schedule an appointment, whatever you need to do. But my hope, my expectation is that you'll go ahead and take the time to do or to try this activity. All right. There is a blank for us to fill in, but I'm 95% confident that you'll know what goes there. All right. So the last thing for us to take a look at in this section is the Pythagorean theorem, which we're all pretty familiar with. So this should go pretty well, followed by a nice, relatively interesting proof of the Pythagorean theorem. So in a right triangle, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. That is, if we have triangle with side lengths A, B, and C, A squared plus B squared is equal to C squared. All right. So let's take a look at a proof of this. And what we're going to do is we're actually going to use similar triangles to help us prove this. And what we're going to do is we're going to take a line through C down to the line AB that's perpendicular. So angle 1 and angle 2 would both be right angles. Of course, we have this angle of this small triangle matches this angle of the large triangle, and that this angle is 90 degrees, matching this angle of the large triangle. So by angle, we would have similarity. Also, this triangle of the, or this angle of the small triangle matches this angle of the large triangle, and this angle of the small triangle matches this angle of the large triangle. So this triangle is also similar to the large triangle. And while that means they're also similar to each other, we won't necessarily utilize that specific observation. But it's the ratios of the side lengths that eventually give us the equation that we're looking for. So, first step, observe the givens. We're given triangle ABC, where the measure of angle C is equal to 90 degrees because it's a right triangle. All right, so let's let CD be perpendicular to AB. And we know that we can talk about it. We know that it exists by the perpendicular existence theorem. All right. So with it being a perpendicular, then the measure of angle 1 is equal to the measure of angle 2, which is 90 degrees by the definition of perpendicular lines. All right. We already said that the measure of angle C is 90 degrees. So by the transitive property of equality, the measure of angle 1, which is equal to the measure of angle 2, measure of angle 1, which is equal to the measure of angle 2, are both equal to the measure of angle C by the transitive property of equality. All right, next we have, let's see here. We want to recognize what we talked about earlier, that the measure of angle CAD is equal to the measure of angle BAC. So we can talk about the similarity of those triangles. So we've got the measure of angle CAD is equal to the measure of angle BAC. And we're using these names very specifically because we want to make sure that we have the corresponding vertices identified. So in this case, we're corresponding C, the vertex C, with the vertex B, vertex A with vertex A, and then vertex D with vertex C. All right. We also have that the measure of angle, this guy here. So for this triangle, we'll call it CBD. This is equal to the measure of angle. We want to keep this angle the same, but this angle becomes the 90-degree angle. So D is corresponding to C, and C is corresponding to say this right here, and C is corresponding to A. Yep, I think that sounds right there. So yes, A, B, C. All right, so both of these are by the reflexive property of equality. So we've also got, once we have that, right, we have whatever angle that we need here along with angle. So we've got the angle conditions for similarity. So triangle ACD is similar to triangle ABC. And this is by side, sorry, not side, angle, similarity. Where we're looking at lines 4 and 5A. And then we also have that triangle C. So we already talked about ACD. We want CBD, similar to triangle ABC as well, again by angle similarity, given in lines 4 and 5B in this case. Excellent. So with that, we can talk about the proportions. Now, let's let this side length from A to D be X, and this side length from D to B be Y. All right. So with the definition of similar triangles, we get that B over X, right? The side, we're looking at A, B, C, side B, and ADC, side X. So B over X is equal to, take a look at this side. Sorry, not this side. We want, yes, C over B. There we go. So B over X is equal to C over B. And we have that A over Y, A over Y. So big triangle, medium side over small triangle, medium side is equal to big triangle, long side over small triangle, long side. Excellent. So this is given by the definition of similar triangles. So again, B over X, we're looking at the short side of ABC divided by the short side of ACD is equal to the long side of ABC divided by the long side of the smaller triangle. And then in the second case, we're looking at the medium side of the large triangle divided by the medium side of the small triangle is equal to the long side of the large triangle divided by the long side of the smaller triangle. If we multiply this equation by bx, right, that removes the fractions and gives us that b squared is equal to cx. If we multiply this equation by ay, then we get that a squared is equal to cy. If I add these two equations together, then I get that a squared plus b squared is equal to, right, pull out the common factor of c, and we have x plus y, cx plus cy, c times x plus y. Once we have that, we should notice that x plus y is c. So x plus y is equal to c by the segment addition theorem. Make that substitution to give us a squared plus b squared is equal to c times c, which is c squared, by the substitution of 11 into 10. That's exactly what we wanted to show. Awesome. So we've seen the Pythagorean theorem, and we've proven it using the tools that we've gotten, that we have seen now in this section. Excellent. So that's it for this section. If you have any questions, let me know. I'll see you guys soon. I hope you have a wonderful day.